Welcome to our deep dive. Today we're looking at this paper called Deep Q Learning versus Proximal Policy Optimization, Performance Comparison in a Material Sorting Task.
Sounds fun.
Yeah, it's really cool research looking at reinforcement learning and how it can optimize those, complex factory processes.
Right.
We're going to break down two pretty powerful techniques here, Deep Q Learning and Proximal Policy Optimization. And we're going to see how they do when you put them up against each other in this simulated production environment.
Yeah, so the researchers actually constructed a simulation that was inspired by a real model factory.
Oh, wow.
Yeah, so it has all the things that you would, see in a real setup. You've got an entry point where all the different parts come in, and then there's this rotary table that directs the flow of materials, and then there's an assembly station.
Oh, cool.
There's stores, there's an exit point, all that.
So like a little mini factory.
Exactly, yeah, like a
Yeah.
mini digital factory mirroring all those complex processes.
Very cool.
And so the challenge for the AI is, two main things. First, they have to assemble the products.
Okay.
So they're attaching rivets.
Got it.
And then they have to sort them.
Makes sense.
So blue products go to the exit and green ones have to be moved over to storage.
Okay.
And what's really interesting is that they tried this before with traditional Q learning in the same environment, and they only got modest results.
Okay.
They could only assemble and sort 1.5 out of 3 products correctly.
Oh, wow. So not great.
Not great, yeah. So the idea here is to see if these more advanced algorithms can really, push the boundaries and improve on those results significantly.
So take it to the next level.
Yeah, exactly.
Okay.
So let's dive into these algorithms a bit, starting with deep Q learning.
Okay.
So at its heart, DQN uses a neural network to try and approximate this thing called the Q function.
Q function.
Yeah, and you can think of this as a guide for the agent.
Yeah.
It kind of predicts the reward they're going to get for each action they could take.
So it's kind of like looking ahead like a chess player.
Exactly, yeah. That's a great analogy. It's calculating all the possible moves.
Awesome.
And it also uses this thing called experience replay, where it basically learns from all its past experiences, what worked, what didn't work. And it uses that to constantly refine its strategy.
So it's learning from its mistakes.
Yeah, just like we do.
That's fascinating.
Right. So then we've got Proximal Policy Optimization, PPO, and unlike DQN, which is all about learning that Q function PPO is directly learning the optimal policy.
Okay.
So it's basically trying to figure out the best thing to do in every possible situation.
So instead of evaluating the outcome, it's learning the best action.
Exactly.
Yeah.
Interesting. And what makes PPO really cool is this balance it strikes between performance and, computational efficiency.
Okay.
So it uses this method called the clipped surrogate objective. And what that does is it limits how much the policy can change during training. So it prevents those really drastic changes and keeps the learning nice and stable, which is super important when you're dealing with an environment as complex as this factory.
So slow and steady wins the race.
Yeah, exactly. If you were learning to play a new instrument, you wouldn't want to completely change your technique every time you practice, right?
Right.
So PPO is taking those small steps and refining its strategy over time.
Cool.
So one of the big challenges in this research was figuring out how to represent state of the factory in a way that these algorithms can understand.
Yeah, because you got to translate that real world into something that AI can work with.
Exactly. That's always a key step.
Right.
So to capture all the complexity of the factory, they ended up using this 101 component vector.
Wow, 101.
Yeah, to represent the state space.
That's a lot.
It's a high-dimensional state space,
Yeah.
which, reflects the challenge of representing this dynamic, interconnected system.
Yeah, you got to make sure the algorithms have enough information to work with.
Exactly. They got to be able to make smart decisions in that environment.
Got it.
So now let's talk about reward design.
Oh,
Because this is a big one in reinforcement learning.
it's how the AI knows what it's doing, right?
Right. It basically tells the agent what it should be aiming for.
Yeah.
So in this study, they looked at 2 different reward functions, R1 and R2.
Okay.
So R1 is all about completing the task.
Makes sense.
So it heavily penalizes collisions. Any incorrect sorting even gives small penalties for inefficient actions.
Okay.
And then R2, it's similar, but it adds this little twist. It includes a small negative reward for every action the agent takes.
Oh, interesting. So like every step it takes is a slight penalty.
Exactly. So it's encouraging the AI to be efficient.
To find the shortest path.
Yeah, exactly.
So R1 is like get it done, and R2 is get it done fast.
You got it.
Got it.
And, designing these reward functions is a really delicate process. It's like you got to find that sweet spot.
Yeah, like training a dog, you got to reward the right behaviors. Cool. So now I'm curious, how did they actually perform? How did DQN and PPO do in this little factory showdown?
All right, so let's look at the results.
Okay.
So the paper shows these key findings in a series of figures.
Okay.
We'll start with figure 4, which shows the training process.
Okay, so we can see how they learn.
And you can see their progress.
Cool.
And what's interesting is that PPO generally outperformed DQN in terms of learning speed.
Oh, so it was a faster learner.
Yeah, it seemed to adapt more quickly to the task.
Gotcha.
Then figure 5 compares how long it took each algorithm to actually complete the sorting task once they were fully trained.
Okay.
And here, PPO, particularly when using that R2 reward function, was much faster.
Oh, wow. So it's not just faster at learning, but also faster at executing.
Yeah, it's efficient.
Very cool.
Then figure 6 shows the success rate.
So how often they got everything sorted correctly?
Exactly.
Okay.
And again, PPO takes the lead, particularly with the R1 reward function.
So PPO is winning on all fronts.
It seems like it, yeah. But there is an interesting little twist here.
What's the catch?
So they found that R2 reward function, the one that encourages efficiency,
Right.
it actually hurt PPO's performance.
Oh, wow. That's counterintuitive.
It is, but here's the thing. That same reward function actually helped DQN.
So the efficiency reward made the efficient one less efficient.
Yeah.
And the less efficient one more efficient.
Yeah, it's kind of a head scratcher.
Wow.
It just goes to show that there's this complex interplay between the algorithm and the reward function.
Yeah, it's not as simple as just picking the best algorithm.
Right. You have to understand how they interact with the rewards they're given.
That's fascinating.
Yeah, it's a reminder that even small changes to the reward function can have big consequences.
You got to be careful what you reward.
Absolutely. Yeah, it really highlights how important it is to understand what's going on inside the algorithm and how it interacts with the reward you give it.
Yeah, you got to pick the right tool for the job.
Exactly. And sometimes it's not just about what performs best in general, but what works best for your specific problem.
So in this case, if you really need speed and efficiency, maybe PPO is the way to go, even if you might lose a little accuracy.
Right.
But if you absolutely need to get it right every time, maybe DQN with that efficiency reward is a better choice.
Yeah, exactly. It all depends on what you're trying to achieve.
This is really giving us a good look at how complex reinforcement learning can be.
Right.
It's not just about the algorithms themselves, but how they interact with the environment and the rewards.
It's like a constant balancing act between exploring new options and sticking with what, works.
Right.
And learning from past experiences while still being able to adapt to new situations.
Yeah.
So before we move on, I do want to mention a couple of limitations that the authors pointed out.
Okay.
So one thing is they assumed a fixed number of products in each simulation run.
Right. Because in a real factory, the number of products coming in would probably change all the time.
Exactly. It's a simplification they made for the research.
Makes sense.
But it doesn't quite capture that dynamic nature of a real factory.
Yeah, the real world is always messier.
Right.
Okay, so what's the other limitation?
So they also limited the simulations to 100 time steps per episode.
Okay.
And that's useful for the research.
Right.
But it might not let the algorithms fully grasp those long-term dynamics of a real manufacturing process.
Because in a real factory, things take time.
Right. There could be delays, dependencies, things that happen over a longer period.
Yeah.
So while the simulation is a good way to study these algorithms, it's important to remember it's still a simplified version of reality.
A starting point.
Exactly. And keeping these limitations in mind helps us understand the results and think about future research directions.
Yeah, like how to make those simulations even more realistic.
Right.
So what are some of the exciting avenues for future research?
Well, one thing would be to look at how these algorithms handle a dynamic stream of products.
Oh, so instead of a fixed number of products, it's always changing.
Yeah, exactly like a real factory.
That would be a lot harder for the AI.
It would really push the boundaries of what we know about reinforcement learning.
So the AI would have to adapt to new products, learn new rules on the fly.
Exactly. It would have to think on its feet.
That's cool.
Yeah. And imagine a factory that can just seamlessly adapt to changes in demand, new products, even unexpected problems.
That would be amazing.
It's like a whole new level of flexibility and resilience.
Yeah.
Another interesting area would be to see how these algorithms scale up.
So instead of a small simulated factory, What if it's a huge one?
Right, because this study was on a relatively small scale.
Makes sense.
So we need to explore how DQN and PPO perform in much larger and more complex environments.
And that makes me wonder if those traditional reinforcement learning approaches would even work at that scale.
That's a good question.
Maybe we'd need to look at other algorithms,
Yeah, like hierarchical methods where you break down the problem into smaller chunks.
like having managers in a big company.
Exactly, each responsible for a different part of the process.
So it's not just about making the algorithms faster, but also smarter?
Right, they have to be able to handle that complexity.
This is really interesting stuff.
It is. It's exciting to see how AI and automation are changing the way we think about manufacturing.
Before we go too far into the future, though, let's take a step back and summarize what we've learned so far.
Okay.
So we started by looking at this challenge of automating a material sorting task in a simulated factory.
Right.
Then we dug into these two deep reinforcement learning algorithms, DQN and PPO.
Yeah, and how they approach learning and decision-making in different ways.
So DQN is like a planner thinking about all the possible outcomes.
Yeah.
And PTO is more like a performer just knowing the best action to take.
Yeah, a good analogy.
And we can't forget about reward design.
It's crucial.
Even small changes to the reward function can have a big impact on how these algorithms learn and how well they perform.
Absolutely.
And we saw that with the unexpected result, that the efficiency reward actually hurt PPO, but helped DQN.
Yeah, it's a reminder that you have to really understand how the reward structure interacts with the specific algorithm you're using.
It's a complex relationship. This has been a really eye-opening look at AI and manufacturing.
Yeah.
It's amazing to see the progress being made and the potential for these technologies to revolutionize how things are made.
It's an exciting time to be working in this field.
Absolutely.
Yeah.
And as these AI agents get better at doing these complex tasks, it makes you wonder what it means for the future of work.
Yeah.
Will these advancements replace human workers, or will they help us do our jobs better?
That's a big question.
It is a big question, and it's one we need to think about carefully as we move forward.
I agree. We need to be proactive and shape the future of work in a way that benefits everyone.
It's about finding that balance between innovation and well-being,
Exactly.
making sure that these amazing technological advancements lead to a better future for all of us.
Well said.
Okay, so before we wrap up, I want to leave our listeners with something to think about.
Okay.
The paper we've been discussing focuses on a fixed set of products in the factory.
Right.
What if the factory had to deal with a constantly changing mix of products?
Oh, that's interesting.
What would that mean for these algorithms?
Well, it would definitely make things a lot more challenging.
Right.
They would have to be able to adapt to new product types, new sorting rules, all on the fly.
It would be like asking the AI to improvise.
Exactly. And that would really push the limits of what we currently understand about reinforcement learning.
It would be amazing to see a factory that could just handle any kind of product that comes through.
Right. A factory that's truly flexible and resilient.
And that's what makes this research so exciting.
Yeah.
It's not just about solving today's problems, but about imagining what's possible in the future.
Absolutely. It's about using AI to transform industries and redefine the nature of work itself.
Yeah, it really makes you think about all the possibilities.
It does. It's a glimpse into the future of manufacturing.
Absolutely. And on that note, I think we've reached the end of our deep dive into DQN and PPO for material sorting.
It's been a great discussion.
It has. It's been fascinating to explore these algorithms and how they could revolutionize how things are made.
Yeah. And I hope our listeners have learned something new about reinforcement learning and how it can be applied to real-world problems.
Me too. Thanks for joining me on this exploration of AI and its impact on the future of manufacturing.
It was my pleasure.
Until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible with technology.